wireless optical biomedical sensing device is a pulse oximeter. Pulse oximeters measure heart rate and blood oxygenation levels. The blood oxygenation level is measured using an optical sensor. The key to pulse oximetry is the difference between oxygenated and deoxygenated hemoglobin and how they react to specific wavelengths of light. Particular wavelengths are 660 nanometer red light and 940 nanometer infrared light. Oxygenated hemoglobin absorbs more infrared light and allows more red light to pass, while deoxygenated hemoglobin absorbs more red light and allows more infrared light to pass. Alternating red and infrared lights are shown at a body location with good blood flow. The calculation for blood oxygenation involves the ratio of red and infrared light seen by the optical receiver, which is in this case a photodiode. A common problem among pulse oximeters is that they are cumbersome to wear, making it impossible to continuously monitor a user. The goal of this design is to make a device small and comfortable enough to be worn throughout the day, and that transmits data to the user's Android phone every 15 minutes via Bluetooth. The data is then displayed in a graphical user interface.
This is the current list of engineering requirements for our project. In this list, the selected requirements focus on two main areas of the system: power and enclosure. The following are two important requirements relevant to power consumption. Must have a battery life of at least 24 hours and must not exceed 500 milliwatts average power consumption. The challenge to these requirements is that they cause design constraints, having a limit on the amount of power required for the system to run on low-power devices. Therefore, the TI-Part MSP430 microcontroller was chosen partly for its advertised low power. The MSP430 is capable of running on 365 microamps during active mode and 0.5 microamps during standby mode. When all major system components are taken into account, the maximum total current consumption in one particular instance is 86 milliamps. Clearly, this number is over-conservative, and the actual values would be smaller because the components of the system will not all run at the same time. However, this number can be used as a good estimate to pick out an appropriate battery. Assuming that the system will sample for 30 seconds every 15 minutes, the system will be active 48 minutes or 0.8 hours in one 24-hour period. With 0.8 hours a day, 86 milliamp peak current, and a 600 microamp idle current, the minimum required battery is 69 milliamp hours. This theoretical calculations satisfies the two requirements because the battery greater than 69 milliamp hours will let the system last at least 24 hours, and the max current of 86 milliamp is multiplied by the 3.7 lithium-ion battery for power. The result is 316 milliwatts, which is less than a 500 milliwatt average power consumption. As for enclosure, the following are important engineering requirements relevant. Must be less than 4 inches on the side. Must weigh less than 0.75 pounds. Must have a case with no external angles less than 90 degrees. Must fit wrist sizes 5 inches to 10 inches circumference. Must operate after being exposed to 10 drops of water on the enclosure. These requirements were chosen to ensure the durability and convenience of the product. Ideally, customers will be doing everyday activities while using this product. Therefore, a comfortable while robust enclosure is required. The biggest challenge in this block will be the size constraint. Being able to fit the whole system comfortably on a customer will require the use of a small but condensed components. With that in mind, all the components in circuitry will be surface mount parts, and the battery, which is the biggest part in our system, will be 1.76 inches by 0.8 inches by 0.3 inches, way less than the limit of 4-inch requirement. Here is a block diagram of the system. The power, battery, and enclosure blocks were discussed in the engineering requirements earlier.
The sensor blocks involve the transmission and receiving of light. The user places the test site, in this case the wrist, against the sensor. The sensor emitter transmits light into the test area, some of which is then reflected back into the sensor receiver. The reflected light is used to determine the blood oxygenation level of the user. The sensor emitter block involves two LEDs, a red LED and an IR LED, chosen for their high intensity relative to their low current draw. Transistors will be used as switches to turn the LEDs on and off, with the timing controlled by the microcontroller using pulse width modulation. The sensor receiver block involves a photodiode and an op-amp. The photodiode chosen is one that is more sensitive to the spectral range presented by the LEDs used, which is 600 nanometers to 1050 nanometers. The output current from the photodiode is affected by how much light it receives, and the current itself is extremely small in the nanoamp range. An op-amp is used as a transimpedance amplifier that converts current to voltage. The amplifier is also needed due to the low amplitude of the signal generated from the wrist compared to the other more common pulse oximeter test sites. The output becomes a signal readable by an ADC. The signal processing block takes the analog voltage generated by the sensor receiver and converts it into a digital signal to be used by the microcontroller. It does this using an ADC, or analog to digital converter. Depending on signal quality, it's possible that the onboard 12-bit ADC built into the microcontroller can be used for data conversion and collection, simplifying the design overall. If it is unable to do the conversions with enough quality and speed, an external low-noise ADC may be used with the same 12-bit resolution. The microcontroller block takes the digital value obtained from the sensor, does some basic processing, and sends it to the wireless block. The microcontroller controls the pulsing of the LEDs as well. The chosen microcontroller belongs to the TI MSP430 line, which is known for its low power and good product support. It also has all of the peripherals needed to connect to the other blocks, including timers for PWM, ADCs for sensor input conversions, and UART for serial communications to the wireless block. The microcontroller code block contains the code necessary to implement all the functionality described in the previous block. The basic flow for the code can be seen in the diagram to the left. The microcontroller will be off most of the time to conserve power. At set intervals, it will wake up, read the sensor with no light, pulse the red LED, and read the resulting sensor data. Then it will pulse the IR LED and read again. After collecting the data, it will send it to the host device via UART-connected wireless block and go back to sleep until the next scheduled collection interval.
The wireless communication block accepts the data from the microcontroller and transmits it wirelessly over Bluetooth to the display device. This is accomplished using a Roving Networks Bluetooth module utilizing serial port profile. This allows serial data to be sent to a paired Bluetooth device, in this case an Android phone. The display device code block is broken up into 3 different subblocks: the GUI, the processing, and the Bluetooth communication. Android has an extensive API for using Bluetooth communications. The diagram on the left shows a general flow of how the code will be written. It is broken up into the server side and the client side. In this case, we will be using the Android phone as the server, and the Bluetooth module will be the client. The first step is setting up the Bluetooth server socket on the server. Once it does that, it will start listening for any connection requests. On the client side, the first step is to acquire a Bluetooth socket. Once the socket is acquired, it will attempt to initiate a connection with the server. Because the server is listening, it will then discover the client's request, and once the connection has been created, you can then read and write between the client and the server. The client will be transmitting the data received from the microcontroller, and the server on the Android phone will be reading that. Once the data has been received, the server and client both terminate the connection. Once another reading has been taken, the server and client will reinitialize, and again, data will be transmitted. To display the data, a GUI will be implemented on an Android phone using Java. A button will allow the user to toggle between displaying their blood oxygenation and heart rate readings. On each screen, there will be 3 main pieces of data displayed. The first will be the most recent measurement taken, allowing the user to see their current level of oxygenation or heart rate. The second will be the average value of the measurements taken over the last day, which will provide a more consistent value for the entire day, accounting for any outliers that may have occurred. Finally, a graph of the measurements taken over the past week will be shown to show any fluctuations that may have occurred throughout the time period. This time period can be toggled between 1 day, 1 week, and 1 month from a drop-down menu.
It's currently week 8, the beginning of week 8 for fall 2011 here at Oregon State. This week we need to finish selecting the parts, which we already started. Week 9 we'll be laying out prototype PCBs for testing those parts. Week 10 our final design specification is due for the course, which is a lot of paperwork for that. Moving on to winter 2012, week 1 we will stuff the prototypes, prototype PCBs, and write the test code. Week 2 we will test the prototypes. Week 3 we'll make design corrections because nothing works the first time, and lay out the final PCBs based upon those corrections. Week 4 we'll design the enclosure. Week 5 we will stuff and test the final PCBs. Week 6 we will integrate the electronics with the software, and then week 7 of winter term we're done.